Welcome everyone to the next installment of our Prague seminar on Cohomology. Our speaker today is Alfonso García-Parrado. He's a lecturer at the University of Cordoba in Spain. Before going to, or returning to Spain, I should say that he was for some time in Prague, actually, at the Theoretical Physics Institute of Charles University. And he's going to talk about an ideal conformally covariant characterization of the Kerr conformal structure. So hopefully explaining a bit in the process. Okay, so please go ahead.
Okay, thank you for the introduction and thank you for the invitation to give this seminar. Well, okay, let me just explain what are the ingredients of this work. The basic ingredients of this work is what we might call an ideal conformally covariant characterization of Einstein spacetimes. Also, and this is the first ingredient. The second ingredient is an ideal characterization of the physical Kerr solution. By the physical Kerr solution, I mean the standard exact solution that was discovered by Kerr, but the rotating black hole. And then we will put together these two pieces, and we will obtain the main result of this work, that is a conformally covariant ideal characterization of the conformal Kerr family. Well, actually, this result, the main result of this work, is the particularization for to the Kerr family of this result. The ideal conformally covariant characterization of Einstein spacetimes that is already known. So I think that when I explain these ingredients, what is the ideal conformally covariant characterization of Einstein spacetimes, then I think it will become clear what I am looking for, what is the aim of this work, and what the main result is. So, to use these ingredients, I will review some elementary notions of conformal geometry, and then explain how they are used for this program. Well, okay, so let us start with the notions of conformal geometry. So suppose that we have a four-dimensional Lorentzian manifold that is used to represent is the mathematical model of our spacetime. I will call this the physical spacetime, and I will denote this with tilde. And then suppose that we have another Lorentzian manifold that that I will call the unphysical spacetime. And the notation is similar, but with no tilde on it. So the situation is that we will assume that there is a conformal relation between the two manifolds, between the physical metric and the unphysical metric. A conformal relation that is written with the convention that is defined with this convention. Okay, so the unphysical spacetime is conformal is a conformal factor times the physical spacetime. And as you know, this relation can be used to define a conformal map and from it we can define a conformal embedding And okay, this is something that has very important applications in general relativity, especially in the construction of the conformal boundary. But here in this work, our interest is this. I'm not going to discuss global issues. This work is only going to be about local issues. Okay, so the important point is this conformal relation, and okay, we will have sets of equations with respect to the physical metric and sets of equations with respect to the unphysical metric. So it is important that we know, or that we are familiar with the relations that are induced by the conformal relation between the physical and the unphysical metric between the geometric objects that we can define for each of them. And so, for example, we have this relation between the inverse metrics. Okay, well, since we have two metrics, we need to have a clear convention about raising and lowering indices. And the convention here is that we use the unphysical metric to raise and lower indices. Okay, so this is the relation between the inverse metrics. This is the relation between the volume elements that are defined for the metrics. Of course, each metric defines a Levi-Civita connection with no torsion, and the relation between the connection coefficients. Well, the difference between the connection coefficients is a tensor, and then this tensor is defined is given by this relation, and we have a relation between the Weil tensor that is defined for each metric, and also a very important quantity that I will define next is the Schouten tensor. Okay, well, an important point that it will be used that it's going to be very important in this work is that some of these relations here are conformally covariant transformations, meaning that it's just we only need to multiply by a suitable power of the conformal factor in order to get the relation between the unphysical and the physical quantity. So, well, as I said, it is important to have in mind that we have two sets of quantities, and that we have relations between both sets of quantities, and another very important idea is the notion of metric concomitant. And for us, a metric concomitant is a quantity that is defined in terms of the metric tensor, its inverse, and the Levi-Civita connection of the metric tensor. So it means that whenever we have a metric, we can formulate, we can define metric concomitants out of it. And since we have here two metrics, the physical metric and the unphysical metric, then we have two families of metric concomitants. Metric concomitants defined with respect to the physical metric, and metric concomitants defined with respect to the unphysical metric.
Alfonso,
yes?
Just to clarify, so your notion of concomitant, so via the dependence on the Levi-Civita connection, you can obtain curvature tensors and then contractions of curvature and covariant derivatives and so on. So that's all included, right?
Yes, exactly. That's all included. Yes.
Okay. All right. Very good.
And then for us there is another notion, this important notion, that is combines this definition of metric concomitant and the fact that we are dealing with a conformal relation between a physical metric and an unphysical metric. And so we get to the definition of conformally covariant metric concomitant. And so we will say that a metric concomitant is conformally covariant if it fulfills this relation under the transformation, and assuming that that we have a conformal relation between the physical metric and the physical metric. Okay, so the situation is that we have two metrics. We can define metric concomitants for each of them, and if both metrics are conformally related, then we have a sort of conformal relation between both concomitants, and this when we have this relation, then we say that the metric concomitant is conformally covariant, and the number p is called the conformal weight of this metric concomitant. We are interested in metric concomitants that are at the same time covariant and conformally covariant. So, we have. If I go back to the previous slide, we have already seen some of these metric concomitants that are conformally covariant. That are covariant and conformally covariant. Okay, so this is one the metric itself, the volume element, and the Weil tensor. Okay, so these are the sort of quantities that are covered by this definition. And okay, so okay, why are these quantities, these conformally covariant metric concomitants important for us? Because we are going to use them to find characterizations, what we call ideal characterizations of families, of conformal families of spacetimes. And this is going to be one of the ingredients that I explained at the beginning of my presentation. Okay, so before going into that, let me just remind you the definition of the Schouten tensor that I have already used, but since we are going to use it for our results, it's important to have it in mind. So, actually, we can use the Schouten tensor to give a characterization of Einstein spacetime. That is going this is going to lead us to one of the main purposes of this work. So this is the definition of the Schouten tensor, and we can characterize an Einstein tensor just by saying that the Schouten tensor is proportional to a physical Einstein spacetime, just by saying that the physical Schouten tensor is proportional to the metric. Okay, so right, if you look at this condition, you can see that this condition is formulated in terms of a metric concomitant. A metric concomitant, because the Schouten tensor satisfies the definition of metric concomitant that I gave before. But the problem with this is that the Schouten tensor is a metric concomitant that is not conformally covariant. And because, okay, as you know, if you do a conformal transformation, the Schouten tensor doesn't have this conformal covariant transformation law that defines a metric concomitant that is conformally covariant. Okay, this is the relation between the physical Schouten tensor and the physical Schouten tensor when we do a conformal transformation. And as we see, this is not a conformally covariant transformation. Okay, so what does it mean for us? It means that the set of Einstein spacetimes is it's not a conformal class in the sense that the Einstein vacuum equations are not conformally covariant. However, this brings us to the one of our main ingredients. The set of Einstein spacetimes are included in a conformal class that has an ideal characterization. Okay, so what do I mean by that? Well, I think that the best is just looking at the results that I want to point out that is one of the main ingredients of this work, and the result is the result given by Gover and Lorentzian in 2006. Although, well, there are some equivalent formulations of this in other references, but I am for me this formulation is especially useful, and the result says the following: suppose that we have a four-dimensional spacetime, and suppose that we define the following metric concomitants of this metric. Okay, so these are metric concomitants. The Schouten tensor is a metric concomitant, the unphysical by tensor is a metric concomitant. So everything there is a metric concomitant. So if this concomitant is different from zero, then our spacetime is locally conformal to an Einstein spacetime if and only if the following covariant concomitant of this metric is zero. Okay. So well, here this TF means trace-free part with respect to the unphysical metric E. Sorry, with respect to the unphysical metric T. Okay. So just for terminology, whenever I have something like a metric with no tilde, I just call it unphysical. Okay. This is just a terminology. And in addition, okay, so here we have a metric concomitant, and in addition, it can be checked that this metric concomitant is conformally covariant, because okay, we have the conformally covariant transformation law that is given here. Okay, so right, so so this is this result in simple terms. What tells you is that okay, if you give me a metric, okay, and you ask me whether this metric is conformally related to an Einstein spacetime, then okay, just do these computations that only involve the metric and compute this tensor. And if this tensor is zero, then you are sure that you can be sure that the metric is conformally related to an Einstein spacetime. So that's for that reason. I mean, for the simple reason that this characterization is given in terms of metric concomitants only, we call it an ideal characterization, and also is conformally covariant. So that's why we call it an ideal conformally covariant characterization of Einstein spacetime. Well, as I said, this is one of the main ingredients of this work, because the main objective of this work, what we want to do is obtain a similar result to this one, but for the Kerr solution. Okay, so the situation is, okay, suppose that you give me a metric and you ask me whether that metric is conformally related to the Kerr solution. So I'm going to give you a set of conditions similar to this one, that's written in terms of concomitants, of metric concomitants. And if those conditions are satisfied, then you can be sure that the metric is conformally related to the Kerr solution. And in addition, each of these conditions are going to be conformally covariant in this sense. Okay, so each of these conditions are going to satisfy these properties. Well, before doing that, let me just give you explain you.
Sorry, Alfonso, just can you go back to the theorem? There was a lot of work in characterizing or rewriting Einstein equations in a conformally invariant way. So like by Friedrich, I think the most famous example, and then some other people put forward slightly different versions. So how is this related to the literature in GR? Because I think Gover-Nurovsky, I mean, they're just like they come from geometry, not from GR.
Yes. Okay. These characterizations of Friedrich that you mentioned, yes, are results that have this a purpose similar to this one, but these are not ideal in this sense, because in addition to concomitants, to covariant concomitants of the physical metric, they involve something else, some other quantities that are, if you want, are quantities defined in terms of covariant derivatives of the conformal factor. If you think of the conformal factor as a gauge quantity, okay, because we are talking here about gauge about conformal transformations, and in the conformal transformations, the conformal factor plays the role of a gauge. Then the Friedrich equations are equations that depend on the conformal gauge, or in other words, the gauge, the gauge quantity, that is the conformal factor, appears explicitly in the equation. In this characterization, you don't have the conformal factor at all. These are, so to speak, gauge-free. This is a gauge-free characterization. Okay, the gauge is only present when you want to study how this condition behaves under conformal transformation, but not in the condition itself.
Okay, I understand. So, but if you remove the kind of the gauge dependent parts from the Friedrich's equations, do you recover like some like these conditions, or are they different but equivalent somehow, or it's just more difficult to relate them?
Okay, I would have to think about it. I think that what I'm going to do next, I'm going to explain you how the proof of this result goes, because it's not very difficult.
Okay.
And then I think that by looking at the proof, one can one might come to an answer to that question.
Okay.
Because what is the proof? Okay, the proof is.
Sorry, just one more aside before you move on. So these equations, obviously they're third order. I can see that the derivative of the Schouten tensor enters into them, or fourth order even. I see. Has anybody studied like the well-posedness of the initial value problem for these equations?
Not as far as I know. Actually, it's one of the open problems that I'm going to mention in the conclusions is just that. So the answer is no, not as far as I know.
Okay, thanks. Yeah, sorry for the interruption.
Yeah, okay. So now about the proof. Well, the proof is just you start from the relation between the unphysical and physical Schouten tensor. And since as I said, the Schouten is not conformally covariant, so you have explicitly the gauge, the conformal gauge in this transformation. And the idea is basically just differentiate this equation and try to remove the gauge using the integrability condition. That's what you do, and actually is a procedure that I think is also used in other parts of geometry. And so I differentiate this equation, I get this, and now this is totally general. And now let's assume that the physical spacetime is in Einstein spacetime. then Shelton tensor, a physical Shelton tensor is proportional to the metric, and then just replace that here, and you get this condition. And the thing is that you can isolate the gauge on this condition just using, but this is as written only works for 4 dimensions because you are using a dimensionally dependent identity. And okay, as I said, you can isolate the gauge in terms of metric concomitants. And right, so if you replace this gauge in your original relation, I mean, so you take this and put it back here and use this relation, and then you get the condition that I showed in Pavel Nurovsky's result, that this this tensor is 0. And conversely, if this tensor is 0, then this implies that you have this condition that when this lambda is one of the concomitants, but also this implies that locally this is an exact differential, and so for some positive for some scalar function, and so you can define a physical metric using this scalar function and do the conformal transformation between your original metric and this physical metric. And this is what I do here. And but the thing is that in this is a special conformal transformation because the gauge from here we see that the gauge is precisely one of the metric concomitants that you have in this condition. So just taking that into account, you realize that this relation between the Shelton tensors turns out to be equivalent to the vanishing of this object. Okay, this is the proof, and just the conformal covariance is proven just by doing an explicit computation. Just compute this E in both metrics, and then you need this intermediate result, and then you realize that indeed this is a conformal. This is a metric concomitant that is conformally covariant. Okay, so right, I don't really know at this point whether Friedrich equations, where you can reduce Friedrich equations to this. I would have to think more deeply, more in detail about it, but I think it's an interesting question. But okay, so the idea now, once we have this more or less clear, the point now is repeat this. Okay, so repeat this, but for the Kerr solution. Okay, so I want to obtain a similar characterization for the Kerr solution. So that brings us to the second ingredient of this work. Okay, I have mentioned this word several times, this ideal word. Okay, this ideal word, what means is that when we are looking for an ideal characterization, I have spoken already about an ideal characterization of a metric that is conformally related to the Einstein spacetime. But now what we need to do something similar for Kerr is we need to start from an ideal characterization of the Kerr solution. Okay, so and here I mean the physical Kerr solution. Now I am talking about the physical Kerr solution. So we need an ideal characterization of the physical Kerr solution, and starting from this ideal characterization, we need to do something similar to what we did for the Einstein spacetime in order to obtain a conformally covariant ideal characterization of the Kerr solution. Okay, ideal in this context has also this meaning. Ideal, we mean okay, in the sense that we have a characterization written in terms of metric concomitants, then the characterization is intrinsic, deductive, explicit, and algorithmic, because okay, we can just take a computer and just do the computations that the characterization tells us to do, and we end up modulo computing power, we can decide whether our metric has the properties that we want. And so, okay, what I'm going to do next is just review an ideal characterization of the physical Kerr solution that was obtained by Ferrando and Saez some years ago, and then I said use this characterization to obtain a conformally covariant ideal characterization of the conformal family of Kerr. Okay, so let me just to explain to present Ferrando and Saez characterization. I need to define some metric concomitants, some physical metric concomitants that are okay, volume element, physical Weil tensor, and then we need to go a bit to the complex world and define physical Weil self-dual tensors, Weil dual and physical Weil self-dual tensors, and okay, we need to introduce some physical Weil scalars. Remember that I am only allowed to raise and lower indices with the unphysical metric, so that's why I need to put all these products of physical metrics, okay, and these tensors. Okay, so all these quantities are physical metric concomitants, and okay, the point is that a Kerr solution is a solution that is a vacuum type D. So we need to find an ideal characterization of type D solutions in 4 dimensions, and this is already available from this result by Ferrando, Morales, and Saez. A physical space-time is of genuine Petrov type D, so it means that it's Petrov type D, but not any of its specialization, if and only if this is true. And okay, all this quantity. These conditions are conditions formulated in terms of metric concomitants of the physical metric. Okay, so now we have we know that Kerr solution is type D, so we already have type D. So we need to narrow down, and for that I need to introduce further metric concomitants. And right, okay, so these are metric concomitants that are defined in terms of Weil self-dual and some covariant derivatives of the Weil scalars. Right. So now with this definition, I can already present the ideal characterization of the physical Kerr solution that was found by Ferrando and Saez. And the idea is okay. We already have an ideal characterization of type D. So what we need to do is we need to narrow down, and okay, if this is true, then we have the family, the subfamily of solutions, type D solutions known as Kerr solutions, and then if we impose this condition, then we get is that the NAT parameter, the so-called NAT parameter, is 0, and so we know that this is Kerr. Well, it's Kerr almost, but we need to add an extra condition in order to get a metric that has Lorentzian signature. And this okay, essentially it's this condition here. Okay, this one is added for regularity, and right. So with these 3 conditions, we are able to narrow down from type D plus, of course, vacuum, the vacuum condition. So with all this, we are able to narrow down from vacuum to all the way down to the Kerr solution. Okay, right. So this, as I said, this is an ideal characterization of the physical Kerr solution. What I want to do next is do the same thing that we did for the ideal characterization of Einstein space-time or vacuum solutions, if you want. That is, try to cast this as a set of ideal conditions, meaning written in terms of concomitance of the unphysical metric, and also in such a way that each of the conditions are conformally covariant. Well, okay, we already have the first step, that is the vacuum condition, thanks to the Pavel and Nurovsky results. And now we have to do the next conditions. Well, some of them are
Sir,
easy
Alfonso,
because, yes?
before you move on, so for those who are maybe not so familiar with the Kerr solution, can you maybe just describe its geometry and interpretation quickly?
Okay. Kerr solution is is the Kerr solution that was discovered by Kerr in the 60s, and it's just the solution that describes a rotating black hole. A rotating black hole that has also what is called a region called when I talk about the black hole, there is a mathematical definition of black hole. That is that it's a solution that is asymptotically flat, so meaning that very far from the source, the space-time is close to flat space-time, and also it has a regular event horizon. You can define a event horizon that is it's the boundary between the asymptotically flat region and the region that is inside the black hole. And remarkably, in 4 dimensions, there are powerful uniqueness theorems about the Kerr solution that tells you that under very strong conditions, the Kerr solution is just the only exact solution that represents a black hole.
So maybe just to clarify, so these uniqueness, the conditions required for uniqueness are approach to flat space-time at spatial infinity. Then you need the stationarity, so that there is a kind of a time symmetry, and there's also a single rotation around a particular axis, so axial symmetry. And under these conditions that Alfonso described, its unique solution, but it also can be characterized by these local equations, as in this case. So sorry, I just wanted to make sure that it's kind of this point is emphasized.
Yes, yes, exactly. Okay, so as I said, the idea now is trying to find something similar, but for the conformal Kerr family. And as I said, we already have the first step, thanks to Pavel Nurovsky's results, and we have to complete just take essentially all the conditions that I mentioned for the physical Kerr. This is type D condition, and then all these other conditions, and put them in such a way that they are written in terms of an physical metric, and they are ideal in the sense that I described before, and conformally covariant. Well, okay, some of this work is easy. This is what I just said. Some of this work is already done, because some of the concomitants that we have used for the physical, for the characterization of the physical Kerr family are already conformally covariant. So it's very simple to obtain this very simple, although some computationally it might require some time, especially if you do computations by hand. But okay, it's conceptually simple to obtain these conditions. So these are metric concomitants that were used in the characterization, in the ideal characterization of the Kerr family. So it means, for example, this one is the one that was used for the type D condition. So vacuum for Einstein spacetime, we just use Pavel and Nurowski results. Then type Z, we use this condition, and this condition is already conformally covariant, so we don't need to do anything else. Okay, there are other conditions that involve these concomitants that are conformally covariant. The problem to make progress is that we have some metric concomitants used in the characterization of the physical Kerr solution that are not conformally covariant. Okay, so when faces a problem similar with a shortened tensor that can be used for the conformally for the characterization of Einstein spacetimes, that shortened tensor is not conformally covariant. So we need this quantity in the ideal characterization of the physical Kerr, and this quantity is not conformally covariant because it has this gauge part here, this conformal gauge part, and so all metric concomitants that you define in terms of this quantity are not conformally covariant. And actually, there are two metric concomitants that are defined in terms of this quantity, and are these two. Okay. Well, I don't need you to remember the precise definitions of all these quantities here. The important point is that they are just metric concomitants of the physical metric. Okay, so what we need to do is we need to basically take this transformation and turn it into something that is conformally covariant and only involves metric concomitants. Okay, this can be done if we just go back to the proof of Pavel's Nurowski results and remember this quantity that appeared in the proof, because this quantity at one point one deduces that this quantity is precisely the conformal gauge. So basically, what you have to do is just use this quantity and add it to the covariant derivative of this metric concomitant, and by doing that, you get something that is already conformally covariant and written in terms of metric concomitant. Okay, so this is a metric concomitant that is conformally covariant. So I need to just replace, just go to this badly behaved metric concomitants and try to write them in terms of this quantity. And this can be actually done if you redefine them. Okay, so remember that I said that there were two concomitants that were badly behaved, and then I just redefined new and physical metric concomitants, and it turns out that these unphysical metric concomitants are conformally related to first of all, these concomitants are conformally covariant, and second, they are conformally related to the badly behaved metric concomitants when they are written in terms of the physical metric. So the conclusion is that we can just rewrite our physical ideal characterization of the Kerr solution in terms of conformally covariant metric concomitants for the unphysical metric, and then get a conformally covariant ideal characterization of the conformal family. And this is the main result of this work. So if there's this an open subset of the so if you give me an unphysical space-time, then there's this an open subset of this unphysical space-time that is locally conformal to the non-trivial Kerr solution, if and only if non-trivial Kerr solution means that it has non-trivial rotation parameters. And this happens if and only if the conditions of Pavel and Nurowski results, together with the following conditions, are satisfied. okay, so this is just that the space-time is conformal to a type D space-time. This is that the space-time is conformal to a Kerr A space-time, and then by imposing this, we get that the space-time is conformal to Kerr, but with with an undefined signature. And then if we want to fix the Lorentzian signature, we need to impose these conditions. And as I said, okay, you don't, well, okay, I just put a slide here, just giving the explicit definitions of all the concomitants, and just checking that they are conformally covariant. But as I say, the important point, I mean, at this stage, it's not necessary to remember these definitions. Just the important point is that remember that these are, if you give me a metric, then I can just put the metric here into these expressions and tell you whether this metric is conformally related to Kerr or not. And then these conditions, all these quantities are conformally covariant. So we have with this result an ideal conformally covariant characterization of the conformal Kerr structure. So conformal Kerr structure, I mean the family of metrics that are conformally related to the Kerr solution. Okay, just to finish, let me just summarize. We have found an ideal conformally covariant formulation of the Kerr conformal class, so a set of conditions that are written in terms of conformally covariant metric concomitants. And okay, so a couple of further research directions. The first one is what Igor asked. Is there a hyperbolization of this ideal characterization or some subset there? I mean, this is of course a more general question is whether what Igor asked is it possible to take Pavel-Mirovsky result and find a hyperbolization, and is that hyperbolization related some way with Friedrich equations, because Friedrich equations are already known to be hyperbolic. Of course, if one is able to find a hyperbolization, then we can formulate an initial value problem for the hyperbolization. Okay, this is another possible research direction is try to formulate all this in terms of factor calculus, because this is a calculus that has a built-in conformal covariance. So maybe there's some sort of equivalent set of conditions, but written in terms written in the factor language. And okay, with this I finish, and thank you for your attention.
So thank you, Alfonso. Okay. Are there any questions? Okay, maybe. So I wanted to ask about basically your construction of the conformally invariant covariant concomitants. If you go back a few slides before the main theorem, yeah, one more. Yeah. So so these new Xi and Z tensors, I guess. So you pointed out that they were not conformally covariant, okay, yes, but they had this transformation rule through the gradient of W that involved well, it involved the derivative of the conformal factor, which you denoted by upsilon, right?
Yes, exactly.
Yeah.
Yes, exactly.
Yeah. Okay. So and the key point in the Gover-Mirovsky result is that they were able to find this metric concomitant lambda, which basically is equal to the gradient of theta, of the conformal factor, when you're not away from Einstein. Because when you're Einstein spacetime, I see the L tensor would be proportional to the metric, and so its derivative would vanish. So on Einstein spacetimes, lambda is 0, right?
Yes.
Yeah. Okay. So I guess I guess that the way that you correct these Xi and W concomitants is that you add something to them which is 0 in the Einstein spacetimes, right? And then because it's proportional to so you add something in terms of lambda, and lambda is proportional to this capital L. Capital L is 0 on Einstein spacetimes. And then so on, I mean, this doesn't change anything on Einstein spacetimes, but once you go to the different elements of the same conformal class, these extra terms that you added, they compensate the conformal transformation, and that's how you get the invariance, right?
Yes.
Yeah.
Yes.
Okay.
Exactly. But also there's another. Yes, that's what you said is true. Is a good description of the situation. But there's another extra point, and it's that when you have this thing, you also get something that is conformally covariant. And a priori, okay, maybe there's some kind of deep geometric reason. There's some kind of deep geometric reason for that. But a priori, I mean, when I look into this condition, I really need to do the computation to check that this is indeed conformally covariant. I don't know whether there is some kind of deep geometric reason that warranties that indeed this is going to be conformally covariant.
Like a deep reason, you mean like some formula involving tractor calculus, which guarantees that the result is conformally covariant, right?
Maybe, but
okay.
Maybe.
Okay, but for me, the reason given explained with the logic that I just described, that this has this transformation property by upsilon, and you want to cancel the upsilon dependence by subtracting something as a function of lambda, right? In such a way that lambda cancels upsilon, and that creates your invariance. I think that's perfectly reasonable explanation.
Okay.
But yeah, of course, okay. Yeah. Once you write down the formula, then you should, of course, be able to check independently of how you found it that it's conformally invariant. Yeah. Okay. Are there any other questions? Okay, that I can see. Just another brief question from me. This result of Gover and Yurovsky, are there other people who have noticed it in the relativity community? Because I don't seem to have come across it before.
No, yeah, okay. There are more people that have worked on this, and actually you can find there is a similar result that, but for any dimension. But what I'm not sure is whether they prove that that the characterization is conformally covariant. But yeah, I mean, it's not just Pavla and Nurovsky. There are other references that deal with this problem of finding what I call what we call an ideal characterization of Einstein's spacetime for any dimension. So it's a problem that people have worked on, and I can, well, in the paper that I have about, well, the paper it's not in the archive. There's a version, but it's not the final version. But there are some references where of previous work about this issue, and yes, people have worked on this, but what I'm not sure is whether they have really checked the conformal covariance of the. Pavel and Nurovsky did. I mean, in the result they state the conformal covariance, but for other people, I'm not sure.
Okay. Yeah, very interesting. Interesting result. Okay. So I don't see any more questions. So let's thank Alfonso again.
Okay, thank you for your
very nice
attention,
talk.
and thank you for your invitation.